Basic principles of electricity. We will start by talking about atom and charge. What is the structure of an atom? An atom is made up of electron, neutron, and proton. The electron is assumed to be negatively charged, while the proton is assumed to be positively charged. The neutron, on the other hand, is neutral. It has no charge. This is an example of a helium atom, and then you can see the electron. You can also see the neutron, and then you can see the proton. The unit of electrical charge is coulomb. And 1 coulomb is usually given as 6.3 times 10 raised to the power 18 electrons. Or you can say that 6.3 times 10 raised to the power 18 electrons is equal to 1 coulomb. So if you divide both sides by 6.3 times 10 raised to the power 18, and then that means you put 6.3 times 10 raised to the power 18 here as a division, and then you also put it here as a division. What you have is electrical charge per electron will be equal to 1 over 6.3 times 10 raised to the power 18 coulomb, and that gives us 1.602 times 10 raised to the power minus 19 coulomb. Let's briefly talk about the charge. The charge is represented as Q when the time is constant. When we have a varying time, we have Q of t. Electrical circuits are used to move charges at desired rate through circuit elements. The motion of a charge is represented with current, while the separation of charge is represented with voltage. The voltage can usually be referred to as electric force, and then current can be referred to as electric fluid. In this course, the convention that we're going to use in general is to assume that positive charge moves to negative charge. This is important because we will use this concept in all our analyses and questions and studies as we proceed. Now, let's quickly look at the mechanical analogy of a charge. So you can see we have height 1, which is a lower height, and then we have height 2, which is a higher height. The difference between height 1 and height 2 is given as delta H. Okay, in the electrical field, the lower height is usually referred to as lower potential, while the higher height is referred to as a higher potential. So what we are saying here is that current flows from the region of higher potential to lower potential. The gravitational force here represents the current. Okay, so on the inclined surface, you see the ball rolling down. That is the ball moving from region of higher height to lower height. In the electric field, this would mean current flowing from the region of higher potential to lower potential. Also, we can use the analysis. We can also represent this analysis using cars flowing in a highway. Traffic current would be equal to the total number of cars we have per minute. And of course, the traffic current will be dependent on how wide the road is and the total number of cars passing through that particular road per time or per minute. The electric current is given as the number of electrons per second, which is coulombs per second, and 6.3 times 10 raised to the power 18 electrons per second is 1 ampere. So you can see electron, flowing down, and as they are flowing down, the convention in general used in the study is that positive charge moves to negative charge, just like we explained the other time. So this is a basic circuit, and you can see we have a voltage, and you can see we have the positive charge at the top. Right at the bottom here is the negative charge. Current flows from positive charge to negative charge. It goes this way. This is a circuit element, passes through the circuit element, and then it goes, and then the flow continues that way. This is exactly what you can see here. Current moving from the region of positive charge to negative, and then it keeps going. The difference between this height and this height is what we refer to as our electromotive force. Let's quickly talk about the voltage difference. What you find here is a pump, and a tap that is supposed to supply water. So at the bottom of the tap, we have P1, and at the top of the tap, we have P2. Somewhere in the middle here, we have the pump. What you notice is that once this pump is opened, water is pumped from the lower region to higher region for it to come out at the tap. And when water gets to the tap here, it flows down into the container based on gravitational force. The difference between P1 and P2 is what we refer to as change in potential. Also, that is exactly what we have here for the electric potential difference. The first analysis here talks about the potential difference, and P1 represents the lower height, P2 represents the higher height. And you can see water flowing from higher to lower potential. The same thing happens for the electrical potential difference. You will see that electrons flow from higher to lower potential. V1 represents the lower potential, V2 represents the higher potential. An electron will flow from the region of this positive charge, which represents higher potential, to the negative charge. And then change in V, which is change in voltage, will then be the difference between V2 and V1. That's V2 minus V1. We also have what we refer to as a ground node or at point. The ground node is a point or junction at which voltage is assumed to be zero. It is usually represented with this symbol, 3 bars just at the bottom, a vertical line with 3 bars at the bottom arranged just the way it looks here. All other voltages take their references with respect to the ground node. And at the ground node, the voltage is always equal to 0. So when you connect a circuit like this to the ground, and we know the ground node is 0, the potential difference connected to that ground node will be equal to 0. In this case, V1 is directly connected to the ground node. So we say V1 is equal to 0. And from the initial analysis we have where we said change in V is equal to V2 minus V1. If V1 is equal to 0, then our change in V would automatically be V2 because V1 will be eliminated. What you can see here is a multimeter that can be used to measure current or voltage. Sometimes it could just be a voltmeter. If it's a voltmeter, then we can only measure voltage with it. If it's an ammeter, you can only measure current with it. But if it's a multimeter, that means we can measure current, voltage, and several other parameters with it. So what you see here is that the black terminal or cable here represents the ground node, and then the red terminal or red cable here represents the measured node. And the measured node could be that you're measuring the current or measuring the voltage or whatever parameter that needs to be measured. So when you get to the lab, you will make use of these a lot in the laboratory, or probably you've made use of it already. Let's talk about current. The current is represented with I when the time is constant, or it could be represented with I of t when the time varies. Current is defined as a rate of change of charge. And that is why you can see we have dq dt. Q represents the charge, dt represents the time. So dq dt is what represents current. The unit of current is ampere, spelled just like you see here, and then represented with A. 1 ampere is equal to 1 coulomb per second. Charge is measured in coulomb, and then time is measured in seconds. So we have 1 ampere is equal to 1 coulomb per second. Current has a magnitude and direction, so you always know where the current is going. It has a direction. It's not going to the right or left, up or down, positive to negative, or negative to positive. So it has direction, and you can always see the direction of movement of current in the circuit given to be analyzed. It also has magnitude, so a value is always attached to it. The total charge entering the element between time 1 and time 2 can be obtained using the integral expression. So you see total charge given as Q total is equal to the integral of I to t from time equal to t1 to time equal to t2. When you integrate this using your basic knowledge of integration, you may need to brush that up so you can follow this concept closely. When you integrate I to t, this gives us Q of t2 minus Q of t1 after you have substituted time equal to T1 and time equal to T2. This integration becomes easier and easier to understand when you know that your I is equal to dq dt. So if you put dq dt here, you can then go ahead and just integrate dq. When you integrate dq, you have just q of t. So when you put t1 and t2 where we have t, then you have q of t2 minus q of t1. We also have the direct current and the alternating current. In the case of direct current, you will notice that the current remains constant irrespective of the variations in time. As the time changes and varies, the current remains constant. That is why you can see that we have a constant line representing the current without any change in the current. But in the case of alternating current, what you would find out here is as the time changes, the current also changes. As the time varies, the current also varies. So we have a wave-like motion, which is usually referred to as sinusoid when we talk about alternating current. So this is what the graph looks like for alternating current. A sinusoid or wave-like motion, and then we have just a constant straight line for the direct current graph. Here is a simple example we can quickly look at. A cylindrical conductor is 1 meter long and 2 millimeters in diameter and contains 10 raised to the power 29 free carriers per cubic meter. The first question says find the total charge of the carriers in the wire. Then secondly, if the wire is used in a circuit, find the current flowing in the wire if the average velocity of the carriers is 19.9 times 10 raised to the power minus 6 meters per second. This is a cylinder, as you can see. This is the length of the cylinder, 1 meter, as stated in the question, and then this is the diameter of the cylinder, as you can see here. It's 2 millimeters in diameter. That means the radius will be 1 millimeter. Okay, so to find the total charge, what we need to do first of all is to find the volume of the conductor. The volume of the conductor will be given as the length of the conductor multiplied by the cross-sectional area of the conductor. The area of the conductor is given as pi r squared from our previous knowledge of mathematics. Multiply that by the length will give us the volume. So pi multiplied by r, our r will be diameter divided by 2. We know that our diameter is 2 millimeter, which is 2 times 10 raised to the power minus 3. Dividing that by 2 will give us our radius. Multiply that by length and by pi. So to find the charge is usually given by volume multiplied by charge per unit volume. So our volume, which is what we have calculated here, pi multiplied by 2 times 10 raised to the power minus 3 divided by 2 all squared multiplied by the length, which is 1, then multiplied by charge per unit volume. The charge on an electron is 1.602 times 10 raised to the power minus 19. That is the charge on an electron. 1.602 times 10 raised to the power minus 19. And then we say that the polarity on electron is usually negatively charged. So that is why this negative is here. Per unit volume, okay, from the question you notice that we were told that the cylinder contains 10 raised to the power 29 free carriers per cubic meter. And we know that we have a volume here. So per cubic meter, that is why we are multiplying this by 10 raised to the power 29. Because we want to know exactly the charge on 10 raised to the power 29 carriers, not just one. So when we do that, we go ahead and then we multiply all these out, and then this gives us minus 50.33 times 10 raised to the power 3 coulombs. So this is going to be the charge contributed by the electrons. Then the second part says we should find the magnitude of the current. So the current will be equal to charge density per unit length multiplied by the carrier velocity. That's how to find the current. We already found the charge density, which is 50.33 times 10 raised to the power 3 from the previous question. Multiply that by the carrier velocity, which is 19.9 times 10 raised to the power minus 6. That would give us 1 ampere. Don't forget, this is charge per unit length, and we know the length of the conductor is 1. So that's what we have, 50.33 times 10 raised to power 3 divided by 1 times 19.9 times 10 raised to power minus 6. If the length of the conductor were to be 2 or 3, you will put 2 or 3 here. So eventually you come up with your current. In this case, it is 1 ampere. Here's another simple example we can quickly look at. Determine the charge entering a terminal between t equal to 2 seconds and t equal to 4 seconds if the current through the terminal is defined by the function. We have the function given here as I equal to t squared minus 2t plus 1. So this is current defined as a function of time. What we would use is the integral fraction we talked about earlier. Our total charge would be equal to the integral of current dt from time equal to 2 seconds to 4 seconds. If you integrate using our basic knowledge of integration, you have t cubed over 3 minus t squared plus t, and then we have the area between time equal to 2 and 4. If you do all of these substitutions as usual with our basic knowledge of integration, what we come up with is 8.667 coulomb. So the charge entering a terminal between 2 seconds and 4 seconds, if the current through the terminal is defined by this function, is given as 8.667 coulombs. Now we will talk about voltage. Voltage is represented with V when the time is constant, or V of t if the time varies. Voltage or electromotive force or potential difference between 2 points A and B is the energy needed to move a charge from point A to point B, and this is usually given as VAB equal to dW dQ, where W represents the work done or the energy, and then we have Q representing the charge. The unit of voltage is volts, and the symbol for that is V. 1 volt is equal to 1 joules per coulomb. The unit of work done is joules, or the unit of energy is joules, and then the unit of charge is coulomb. So that's why we have 1 volt equal to 1 joules per coulomb. But then we do know that our work done is equal to force times distance. So force represents Newton, while distance represents meter. That simply means we can rewrite these as 1 Newton meter per coulomb. Now for this study, we are going to focus on some general conventions, one of which is when we have two terminals, you can see we have a terminal, another terminal here. The potential difference or the voltage across a circuit element is given as V. In this case, V naught, it can be V naught. And then we have a positive charge right up here and the negative charge. So if we have two terminals A and B with the reference A and B, so terminal A is here and terminal B is here. So the potential difference or the voltage across the circuit element between those two terminals can be represented with VAB. So you can see we have VAB here. All right. Now, when energy is consumed by the circuit element, that means current flows into the circuit element. So energy consumed by the circuit element indicates that current flows into the circuit element from positive to negative. This is very important. So also you can see here that current is flowing from positive charge to negative charge. When we have this kind of a scenario, it means energy is consumed by the circuit element. But when current flows out of the circuit element, it simply means that energy is delivered by the circuit element. This is very important because we would apply this concept in most of the analysis that will be conducted in this study. So you can see current going from negative to positive here. This means energy is delivered by the circuit element. Current is going from negative to positive. You can see that here. Energy is delivered by the circuit element. When you look at the equivalence between mechanical and electrical energy, what you will notice is that mechanical work is equivalent to electrical work. In both fields, these are the various representations that are equivalent. Mechanical energy is equivalent to electrical energy. What you can see here is a force being applied by an object, in this case a horse or two horses, what you would find out here is that we have a wagon initially at this position, and then a force was applied to the wagon. A force of 1 Newton was applied to move the wagon from this position to this position through a distance of 1 meter. In this particular case, the mechanical work done will be equal to this force multiplied by the distance, and that will give us 1 joule, as you can see here. And then the equivalent of that in the electrical field will be representing this scenario with this circuit, and then the electrical work or electrical energy would now be equal to 1 joule. 1 joules per second is equivalent to 1 watt. This simply means that we spend 1 joule within 1 second. So when we say 1 joule per second, so if you rearrange this, it means that 1 joule will be equal to 1 watt second if you cross multiply. And then the other unit of power that we have is horsepower. 1 horsepower is usually given as 746 watts. So in case you have 2 horsepower, that will be 2 times 746 watts. If you have 10 horsepower, that will be equal to 10 times 746 watt. That's how to carry out such conversion, because we may need to do that as we move on. If you're looking for power, 1 joule per second is equal to 1 watt here. 1 joule per second is equal to 1 watt here. Okay, so we've talked about energy, we've talked about power. Let's quickly define power now. Power is usually given as the multiplication of voltage and the current. So power is measured in watt, and it is equal to voltage times current, which is volt times ampere. And then this is a simple circuit to show you we can always calculate power delivered or power consumed by a circuit element. Power is represented with P when the time is constant and with P of t when the time varies. Power is the rate at which work is being done, and it is given as dW dt, where W represents the work and T represents the time. When we say rate, we are referring to time. It takes something to happen. So this dW dt can also be rewritten as dW the Q dot dQ the T. You will notice that the identity of this dW dt is kept when we divide this dQ by this dQ. When we cancel these two dQs out, we go back to the initial definition, which is dW dt. So it means these two definitions are the same here. They are equivalent. Moving on from that point, you will notice that we had said at the beginning that dW dQ represents our voltage, that is work done over charge, and then dQ dt, which is charge over time, is represented with current. So that means we can say that our power will now be V multiplied by I. That is how we got this VI here. The unit of power is joules per second. We mentioned that earlier, or it can be watts. They mean the same thing. Energy delivered to an element between time 1 and time 2 can also be calculated using our integral function. So we have time 1 and time 2. From time 1 to time 2, the total energy from time 1 to time 2 is given as integral of T1 to T2 of P dt. P represents power. Okay, so if you bring VI here, you know what VI is, that is dW dt. If you integrate that, what you would obtain is W of T. So if you substitute your time 1 and time 2 into W of T, using our knowledge of integration, what you would have is total energy delivered to an element would be equal to WT2 minus WT1. That is work done at time 2 minus work done at time 1. Again, we're going to use the following conventions. First of all, you should note that in a circuit, the summation of all the powers in a circuit is equal to 0. And then the element is consuming, the circuit element we have in a circuit is consuming power when current flows from positive to negative charge. In this particular case, the power is going to be positive. So you have P equal to V multiplied by I. It will have positive polarity because current is flowing from positive to negative. As you can see here, irrespective of how you decide to arrange these, as long as the polarities are properly positioned. Okay, here current is flowing down, but it's from positive to negative. Here current is flowing up, but then it is also from positive to negative. The element is delivering power. The circuit element is delivering power when current flows from negative to positive. So you can see current flowing from negative to positive here. In this particular case, the polarity of the power will be negative. So you have minus VI. This is important. Please pay attention to these conventions. Let's quickly look at the passive sign convention. When current through an element is in the direction of the reference voltage drop across the element, a positive sign should be used in expressions relating the voltage to the current. We just talked about that in the previous slide. And then there are standard prefixes for powers of 10 that you should pay attention to, so that when we start some analysis, you will understand how to make some conversions and how to represent what needs to be represented. So you will see we have centi represented with the symbol of C when the prefix is centi. For example, if we have meters, that means we have centimeters. Okay, so the prefix is centi and the symbol is C. It could be milli, which is 10 raised to the power minus 3. Centimeters or centi represent 10 raised to the power minus 2. You can see pico representing 10 raised to the power minus 12. R2 representing 10 raised to the power minus 18, and then you can see there are various symbols here. It goes all the way to 10 raised to the power minus 1 and down to 10 raised to the power 12. 10 raised to the power 12 can be represented with prefix tera, and the symbol is T. And then giga is represented with the symbol G, which is 10 raised to the power 9. All right, and then that goes on to 10 raised to the power minus 1, which is deci, and represented with the symbol D. The prefix is deci. All right, please pay attention to this too. Electrical energy, by definition, is equal to power times time. That would mean watt times second. So electrical energy can be, the unit of electrical energy is equal to watt seconds. Okay, you can also convert that to hours. For example, we could have kilowatt hour. Kilo means 10 raised to the power 3, like we mentioned in the previous slide. And then this hour can also be converted to seconds, and seconds can be converted to hour. So in this particular case, when the time is measured, when the power is measured in kilowatt and the time is measured in hour, we have kilowatt hour. Okay, this time can always be converted to seconds, and these kilowatts can always be converted to watt by multiplying. To convert kilowatt to watt, you multiply by 1000. To convert hour to seconds, you multiply it by 3600. How did we come about this 3600? 1 hour is equal to 60 minutes. 1 minute is equal to 60 seconds. 60 times 60 gives us 3600 seconds. So the conversion is pretty much straightforward. 1 kilowatt hour would be equal to 1000 times 3600 watt seconds. And this gives us 3,600,000 watt seconds or joules. That's what we do have here. Okay, as we mentioned earlier, 1 kilowatt is 1000 watts, 1 hour is 3600 seconds. So energy is equal to power times time. This is important, pay attention to it. There is a simple example that we can quickly use to demystify all the explanations that we gave. Calculate the monthly payment for the energy consumed by the lamp shown on the right hand side. This is the lamp we're talking about here. This is the lamp here connected. So the source voltage is 220 volts. The current drawn by the lamp is 5 amperes. Price of electricity or price of electrical energy is 12 cents per kilowatt hour. So what we're looking for is the monthly payment for the energy consumed by the lamp. First of all, we have to go from hours to day and then to months. So let's see how we deal with this kind of questions. The power is equal to voltage times current. We mentioned that earlier. So we know our voltage is 220 volts, and then we know our current is 5 amps. So total power is equal to 1100 watts. We keep that somewhere. Energy is usually equal to power times time. Since we know our power to be 1100 watts, we bring that straight up here. How do we know the time? Since we are dealing with monthly payment, we have to find out the total time in the month. Total time in the month would be 24 hours in a day and then 30 days in a month. So you have 24 hours per day multiplied by 30 days per month. That will give us the total number of hours that we're talking about in a month, because we're looking for monthly payment. So this becomes 1100 watts multiplied by 24 and then multiplied by 30, and that gives us 692,000 watt hours. This can be converted to kilowatt by just dividing this by 1000, and that gives us 792 kilowatt hours. If we proceed from here, monthly payment will then be, since we are looking for monthly payment, it will then be 792 kilowatt hour, which is total energy consumed in a month, 792 kilowatt hour multiplied by 12 cents per month. If we multiply that out, what you would have is $95 per month. Another example, a stove draws 15 ampere when connected to a 120 volt line. How long does it take to consume 30 kilojoules? This should also be straightforward for us. We do know that our power is equal to voltage times current, and that will give us 120 volt multiplied by 15 amperes, and that's about 1800 watt. Convert this to kilowatt if you so wish to do that. You divide this watt by 1000, and that gives us 1.8 kilowatt. We also know that our energy is equal to power times time, as mentioned earlier. So to find the time that it takes to consume 30 kilojoules, what we will do is just rearrange that formula, and that gives us time equal to energy over power. Our energy is given in the question as 30 kilojoules. We put that here. Our power has been calculated right up here as 1.8 kilowatt. You put that here. 30 kilojoules is the same thing as 30 kilowatt seconds. So kilowatt will cancel kilowatt. We're left with seconds, and then 30 over 1.8 will be equal to 16.667. So overall, total time taken to consume 30 kilojoules by the stove will be equal to 16.667 seconds. Here is another example. A notebook computer has a total power consumption of 70 watt when running an average application. The battery used in this notebook has a capacity of 300 watt hours. What is the average battery life of this notebook? Again, we know that our time is equal to energy divided by power. In this particular case, the energy is usually given as the battery capacity. So we know that is equal to 300 watt hours. And then we have that here divided by the total power given as 70 watt. And that will be equal to 4.3 hours. This is also straightforward. When we say average battery life, it means the time to take the battery to be discharged, and that will give us about 4.3 hours from the calculation we just made. So pay attention to how to use watt hour, how to use watt seconds, how to use kilowatt hours, how to use different variations of the units that we have. This is the end of this lesson. If you enjoyed this video, if you like this video, I want to encourage you to give it a thumbs up. I would like you to also subscribe to this channel and hit the notification button so that whenever I upload new videos, you can easily get the notification and have access to the videos immediately. I would also like to know what you think about this video. So feel free to drop a comment in the comment section. Let me and others watching this video know what you think about this video and lesson. All right, do have a wonderful time, and I'll see you in the next lesson.